In this video, you will learn about scientific notation. You will learn how to convert a number from normal or standard notation to a scientific notation. And then you will learn how to convert a number from scientific notation to a normal or standard notation. Before we learn what is scientific notation, let's have a background on why we need scientific notation. In science, we deal a lot with the measurements, and the measurements are often very large or very small. For example, the number on the screen is the estimated number of cells in a human body. This next number that I have is the estimated number of atoms on Earth. And this number is the width of a human hair, a very small number. And the last example that I have is the mass of an electron in grams. So look at all these zeros. These are very large. Some are very large and some are very small numbers. And they are not only a lot of work to write down because of all these zeros, but they are hard to work with as well. It is not easy to analyze them. And just imagine that if you have to do multiplication or division or any other math operation on these numbers, it would be very difficult to do with all these zeros. Just making sure that you have included all the zeros on your calculation and you have not forgotten any zeros is really a big pain. So a scientific notation can actually help us out here. And instead of using all these long sequence of long zeros, scientific notation help us get rid of all these zeros and write these numbers in a shorter and compact way. So let's see what is scientific notation. Scientific notation is scientific notation is the expression of a given number as a power of 10 times a number. And the general form of a numerical quantity written in scientific notation is actually A times 10 raised to the power of x, where this A is called significand because this A will always indicate significant figures without any doubt. And this x will be indicating the powers or the zeros that we have in the actual normal notation. So now the benefits that we can get out of scientific notation is that writing a measurement in scientific notation is not only converting a very large or a very small number to a convenient and workable number, but it also helps us indicate the uncertainty in the measurement. And you will see this when we will do examples, what it means. So let's look at these numbers that we saw in one of the previous slides, a very large number and very small numbers. Let's see how they look like when we write them in scientific notation. Looks much better, right? Here we have normal notation, right? And we have the scientific notation. These black numbers are the scientific notation. So these two numbers are just two different ways of writing the same measurement. These huge numbers or the small, tiny numbers with a lot of zeros are equal to these compact scientific notation forms, where the power of 10 indicates the number of places or zeros in this measurement. So these numbers, the scientific numbers written in the scientific notation are much easy to analyze, much easy to work with. So let's see how to convert a number from normal notation to a scientific notation. The first thing that you have to do here is you have to find number of significant figures in the normal notation. And we already have learned the rules on finding the number of sig figs, so we will use those rules to find that. The next step is you have to find decimal point in the measurement or in the number. Sometimes it is very obvious to identify that number, but sometimes it is not written. If it is not written, you have to remember that it is always at the end. We just don't need to show it if there aren't any other decimal digits after that. So for this step, if you have to find the decimal point, then that decimal point is here at the end. The next thing is you have to move the decimal point after the first non-zero digit. So the first non-zero digit in this measurement is this one, right? So this is your first non-zero digit. You have to move this decimal point right after this. So what we're going to do, we're going to move this like this, right? And we're going to move this decimal point here. And this is what we did here. Okay. Next step is you have to multiply this number. So this number that you have, 1.23, is your A, this number, right? So this is your A. So you are done with your A, and next step is you have to multiply it by the value of 10 times x. This x will be the number of places that you moved this decimal point. So here we move the decimal point by 2 places to the left. So this 10 to the x is 2. And converting this 123 to a scientific notation, your answer will be 1.23 times 10 to the power 2. One thing that you can remember by when you are converting a normal notation to a scientific notation is you have to remember which way you are moving your decimal point and what will be you are going to do with the exponent. If you are moving the decimal point to the left, which we did in this case, we moved the decimal point to the left, right? So if you're moving the decimal point to the left, the exponent will go up. What does it mean? The exponent will go up. So the exponent, there is always, even in this normal notation form, you have to remember that there is always a 10 to the 0 there. This 10 to the 0 means 1, right? So your 123 multiplied by 1 is just 123. But you have this 10 to the 0 here. So you are moving, if you are moving the decimal point to the left, you are moving this exponent up. Up means it will go in some positive number like 1, 2, 3, 4. And since we moved the decimal 2 places to the left, our positive number is 2. But if you have to move the decimal to the right, then this exponent will go down. Means if it was 0 in the beginning and you are moving it to the right, then it will go in negative numbers like -1, -2, that type of number. We have some more examples to learn it better. So in this example, we have 0.00295. Remember, the first step is you have to identify number of significant figures. In this measurement, you have 3 leading zeros, and leading zeros are never significant. So your sig fig in this will be 3 sig figs, right? So you identified your 3 sig fig, and this 3 sig fig is what you are going to show in your A. Okay. Step number 2 is, okay, let me write it down this number here so that we can work with it. Okay. Step number 2 is you have to move this decimal point right after the first non-zero number. Your first non-zero number is 2. So you are moving this decimal after this 2. So I'm moving it to the right, right? So my decimal will come here. Okay, so after moving this decimal, I will write my A, how this A will look like. So my A will look like 2.95, and then I will check, am I showing the correct number of sig fig? My actual measurement have 3 sig fig. Am I showing 3 sig fig in A? And you can see, yes, it has 3 sig figs. The next thing is I will multiply it by 10 to the x, and my x will be the number of places that I moved this decimal. So I moved this decimal 3 decimal places, so it is 3. Now what will be the sign? So for the sign, I move the decimal to the right, so my exponent will go down. So go down means my exponent will be in negative. So converting this normal notation to scientific notation, you will get 2.95 times 10 to the negative 3. Let's look at another example. Okay, we have these so many zeros here, and we have to convert this number to scientific notation. Our first step is we have to identify number of sig figs. In this measurement, we have 3 trailing zeros, but there isn't any decimal point. So trailing zeros without a decimal point are not significant, right? So in this measurement, if I have to write how many sig figs I have 4 sig figs. So this 4 sig fig will be what I will show in my A. So let's write down this measurement here, and then we are going to work with the decimal. So decimal point is not written in this measurement, but we know that if it is not written, it is always at the end. But this decimal point is what I am writing, and by writing this decimal point, it will not change the significant figures that I already have identified here, right? By writing this decimal point, just to convert it to scientific notation will not make these zeros significant, okay? So I write it here, and now I'm moving this decimal point. So 1, 2, 3, 4, 5, 6. I'm moving it 6 places to the left. So now I am writing it down. And when I'm writing my A, this significand, it is called okay. So I'm writing 3.952, right? And I'm not going to write these zeros because I have to show 4 sig fig, and these zeros were not significant in the original measurement that was given. So this will be my A, and after that I need to find what it will be my X. So my X will be 6. What will be the sign with this X, positive or negative? I moved my decimal to the left, so my exponent will go up, means it will be a positive number. So this will be my scientific notation for this problem. Okay, here we have another example. In this example, remember again, our first step is to find number of significant figures. So this measurement have actually leading zeros here and a trailing zero here. So leading zeros are never significant, and trailing zero is significant if there is a decimal point in the measurement, which we have here. So this measurement actually have 3 significant figure, because this trailing zero is significant as well. So that was my first step, that I identified my significant figures, and now I have my number, and I have to move this decimal point right after the first non-zero number, which is 1. So I moved it to 4 decimal place, and after moving it, let's write down our A. A should have 3 significant figures, because that's what we have in our original measurement. So 1.80, and then you are going to do 10 to the X will be 4. Let's see which direction we moved. We moved it to the right, and the exponent will go down. So my exponent is going to be -4. Now let's do some practice on converting a scientific notation to normal notation. Remember that in normal notation, you have a measurement multiplied by 10 to the 0. This 10 to the 0 means it is 1, right? So you have a number multiplied by 1. So, and we normally don't write this because it doesn't add any value to this normal notation, right? But when we are converting this scientific notation back to normal notation, what you need to know is that what you actually doing is converting this exponent back to this zero place, right? And when you are converting back to the zero place, you will again go here and see what you are actually doing. So you are moving this 4 to 0, means your exponent is going down. So if your exponent is going down, you will be moving your decimal point to the right. So I have this measurement. So I will just write down this A because now I have to convert this A back to our normal notation form. So I have my 8.79, and I have to move this decimal to 4 places. And which direction I have to move, because I'm making it down, I have to move it to the right. So I will be move this decimal to 4 places to the right. So I moved it, and now my decimal is here, right? So when I'm moving, if you have places where there isn't any digit, you will be just simply adding zeros here. So after moving the decimal to the 4 places to the right, you have your number 89700, and this is your final answer. But what you need to remember is you have to make sure that you are showing the exact number of sig figs that you have in the first measurement. So the first measurement have 3 sig figs, right? And when you are ending your answer, your normal notation is also 3 significant figure. This decimal point that you move to the right is only for converting the scientific notation to the normal notation, but you are not going to show that decimal place here, because if you do, then it will make all these zeros significant, and then you will end up having 5 sig figs that will be incorrect. Okay, so this will be your correct answer, but if by accident you are leaving your decimal at the end like this, that will be your incorrect answer. Okay, because this will have 5 sig figs, and this is 3 sig figs, and you are getting these sig figs from here. Okay, let's do one more example here. So in this example, you have to convert 4.3 times 10 to the negative 2 to normal notation. So remember again, you have your normal notation that always have your 10 to the 0. So you're making this negative 2 to 10 to the negative 0, means your exponent is going up, right? From negative 2 to 0, your exponent is going up. So you will be moving your decimal to the left. So your notation that is given, your A is 4.3. So we will start from A and then move this A to the 2 places to the left. And here is my 2 places to the left. I will add a decimal here, and the places where there isn't any number, I will add zeros. So my normal notation here will be 0.043. Okay. Let's do some more examples. Okay, here you have to write the following numbers in normal notation. So you have some exponential forms given, and you have to convert them to the normal notation. And again, your normal notation is a number, and it is multiplied by 10 to the 0. So you have this negative 6 exponent here. You are converting this negative 6 to 0, means your exponent is going up. So you will be moving this decimal point to the left. So let's write your number and then move it to 6 places. 3, 4, 5, 6. And here is your decimal point. You will write zeros for the places where you don't have any digit, and it will be 0.3, 4, 5, 6, 4, 0, 0. So remember how many sig figs you have in this measurement? You have 3 sig figs, right? And how many sig figs you are showing in this measurement? You are showing 3 sig figs. These leading zeros are not significant. Okay, so remember in science, when we do a conversion from one form to another form, or we are using these numbers in mathematics, we don't change the significant figures. We start with the number, certain number of sig fig, and we end with the same number of sig fig. Okay, let's do this example. In this example, again, you have -3, and if you have to convert it back to 0, means your exponent is going up, so we will be moving the decimal point to the left. So you have 2.35 is your number, and you are moving this 3 places to the left. You have your decimal here, and you are adding some placeholders, some zeros where you don't have any digits, and your measurement is 2, 3, 5. Let's check our significant numbers. We have 3 sig figs here, right? And at the end we have 3 sig figs here. Okay, these are your leading zeros. Let's do this last example now. The last example that we have is 6 and 10 to the 3. So making this 10 to the 3 to 10 to the 0 means your exponent is going down. So if exponent is going down, you will be moving the decimal to the right. So your measurement is 6, and there isn't any decimal given, but we know that that decimal is always at the end. So I will write the decimal here, and then I move it 3 places to the right. So 1 place, 2 place, and 3 place. So by moving it 3 places, I have it like this, right? I moved the decimal from here to here. Now I have to write this in a normal notation, and I don't want to change my significant figures as well. In this measurement, I have 1 sig fig, and here I have 1 sig fig because there isn't any decimal point at the end. If by mistake I leave this decimal point that I moved here, that will be incorrect. Like for instance, if I leave it like this, that will be incorrect, because by making this, I'm saying that we have 4 sig fig. That will be incorrect. We cannot have 4 sig fig starting with 1 significant figures. So that we have a practice. Now let's see one more example. It has a little bit more information, more words that we need to use to solve this problem. So this problem is that it's a multiple choice problem, right? So you have to, so which of the following is the correct scientific notation for this very large number, assuming that uncertainty to be is in plus minus 1 million years. So this is something extra information given. Before, in the previous examples that we did, we had some examples we did. For instance, this one, where the decimal point, there was no decimal point here, right? And no extra information given. So we knew that this have only 4 sig fig for sure, and these zeros are not significant. But in this example that we are doing, there isn't any decimal point, right? So without decimal point, we only have 3 significant figures if we do it in a normal way. But there is some extra information given that the uncertainty is in plus minus 1 million year. And remember that the last uncertain digit is also a significant digit, right? And that uncertain digit is the digit that we are making the estimate of. So let's count that column, and then that will be our last column that will be significant. So this is your ones, tens, hundred, 1,000, 10,000, 100,000, and this is your 1 million column, which means that this is the column where we made our estimate. And from here, all these digits, these are your significant digits. So if you count sig fig under this, we have 3, 3, 6, and 7, 8. So we have 8 significant figures here. So if we are converting this number to a scientific notation, let's see how it will look like. Okay, there isn't decimal point. We will make the decimal point at the end. We have to move this decimal point right after the first non-zero number. We are moving it to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we are moving it to the 13 places to the left, so it will be positive 13. So we know what our exponent going to be. Now let's see what are we going to write in our A. Remember that A will have the significant figures. It will show all the sig figs that we have in this measurement. And we identified that this measurement have 8 significant figures. So you will show 4.710012. So now we have 3, 6, 7, 8 significant figures. So this will be your answer when you are converting this normal notation to the scientific notation with proper number of sig fig. You are starting with 8 significant figure and you are ending with 8 significant figure. So this is all you need to know about scientific notation for your Chem 108 course. I hope this video is helpful for you.